In this lesson, we're going to be identifying and evaluating exponential functions, graphing exponential functions, and solving real-life problems involving exponential functions. An exponential function is a nonlinear function of the form y equals ab to the power of x, where a does not equal 0, b does not equal 1, and b is greater than 0. As the independent variable x changes by a constant amount, the dependent variable y is multiplied by a constant factor, which means consecutive y values form a constant ratio. Another way to say that is every time we increase x by 1, I'm multiplying my y value by the same thing. For this example, we want to figure out if each table is representing a linear or an exponential function. Then we need to explain why. So for part A, I see that I am adding 1 each time for x, okay, and then I'm adding 2 each time for y. So every time I increase my y value, I'm adding 2. And we know that that's going to be a linear change, right? Because I'm adding 1 in the x, adding 1 in the y. That's a constant rate of change. So this one's going to be linear. Now for part B, once again, I'm adding 1 for x each time. But if you look, each time I'm looking at y, I'm multiplying by 2 here. Times 2, times 2, times 2. So since I am multiplying by the same number each time, aka I have a constant factor of change, this is an exponential function. And now we're done with this one. For this example, we want to evaluate each function for the given value of x. Okay? Well, I have y equals negative 2 times quantity 5 to the power of x when x equals 3. So all I'm going to do here is plug in 3 for x and then simplify. So I have y equals negative 2 times 5 to the third power. Okay, order of operations, I'm going to do 5 cubed. Well, I know 5 cubed is 125, but if you didn't, you could do that out. 5 times 5 times 5. So that's going to be negative 2 times 125. Well, if I double 125 and then make it negative, y is equal to negative 250. Now we're done with part A. For part B, I'm going to do the same thing. I'm going to plug in my x value. So I get y equals 3 times 0.5 to the negative second power. If you remember, this negative exponent really means that I can flip this. I can put this on the bottom of the fraction. Okay, so this is really going to become 3 over 0.5 squared. Okay. Well, I know 0.5 squared is 0.25. That's 0.5 times 0.5. So now this here I have 3 over 0.25. Okay. Well, I can multiply 4 on the top and bottom to cancel this 0.25 out. Okay, and that'll just become 1. So really this just simplifies to 3 times 4, which is going to be 12. So that is the answer for part B, and now we're done with this one. Graphing exponential functions. The graph of a function y equals ab to the x is a vertical stretch or shrink by a factor of the absolute value of a of the graph of the parent function y equals b to the x. When a is less than 0, the graph is also reflected in the x-axis. The y-intercept of the graph of y equals ab to the x is a. So in this case, we have 2 scenarios. We have when b is larger than 1, okay, so when my b value is greater than 1, it looks like this if a is positive, the blue graph, and then the red one is if a is negative. And then here, if b is in between 0 and 1, okay, so 0 is less than b is less than 1, I have 2 other scenarios. Okay, so if a is positive here, we have the blue graph. And if a is negative, I have the red graph. Graph f of x equals 4 times 2 to the power of x. Compare the graph to the graph of the parent function. Describe the domain and range of f. All right, so whenever I'm graphing and I'm feeling unable, I can make a table. I like to say that phrase. Okay, so I'm going to make a table of values here. So I have x, and then I have f of x. And let's see, I want 5 spaces. I would basically like to start at 0 in the middle, and then have 2 more x values to the right and 2 more to the left. I'm going to do 0, 1, and 2, and then -1 and -2. Okay, so what I like to do is always start with 0 because that's the easiest number to plug in. So I'm going to plug in 0 here. 2 to the power of 0 is 1, and then 1 times 4 is 4. Okay, and then if I plug in 1 next, that's the next easiest to plug in. 2 to the power of 1 just stays 2, and 2 times 4 is 8. And I know this is an exponential function, so I can just see the pattern here. I'm multiplying by 2 each time. Okay, so this is going to be 4, 8. This one will be 16. And then I'm dividing by 2 each time going to the left. So this one's going to be 2. This one's going to be 1. Okay, so I'm going to plot all of these ordered pairs. Okay, and notice I'm counting by 2's here. So I'll start right here. This is going to be -2. That'll be 1, which will be halfway up. And then this will be -1, which will be up to 2. And then 0, 4. And then 1, 8 will be right here. And then 2, 16 be right there. Okay, so what I want to do now is I want to draw a smooth curve through this. Okay, and one thing we can do if we don't trust ourselves to draw a smooth curve is you can kind of sketch a thin curve here. So something like this. And then our exponential function will approach 0, but it will never cross this axis right here. Okay, so if you had a computer software doing this, it would give you a smooth curve, but you can sketch a curve like this too. If you didn't want to sketch the graph like I did, you can also just try to draw a smooth curve through this. So if you can see my screen, something like this. Either will work, but I think the sketch probably gives you more of an accurate representation of what the graph actually looks like. But it would look better if you did a perfectly smooth curve, but I often am unable to do that, so that's why I do the sketch. Anyway, now that we're done graphing this, we want to compare this to the graph of the parent function. If you remember, the parent function is just this function without the multiplier. So this a value right here is 4. That's being multiplied to my number being taken to the x power here. So basically, my parent function here, I'll call that g of x. That is just going to be 2 to the power of x. Okay? Now to graph that, I can make another table as well. And I like to have 5 values. Okay? So I'll put 0 here. 1, 2, -1, and -2. Okay? And then 2 to the power of 0 is 1. 2 to the power of 1 is 2. 2 squared is 4, and then going the other way, I'm dividing by 2, so I can know this is going to be 1/2 and 1/4. I will graph this in red. Okay. Now I'm going to sketch my graph that I've plotted my points. So something like this. So if you can see, because I multiplied the function by 4 here, the parent function by 4, okay, this is actually going to be a vertical stretch. Every single point on the red graph is stretched by a factor of 4 to get to the black graph here. Okay, so this value I go from 1 to 4. Here I go from 2 to 8, and then here I would go from 4 to 16. Okay, and so on. That would be the case for every single point on this red graph. Okay. Now I need to describe the domain and the range of this function. Okay, and the original function here. Well, the domain is all real numbers. I know I can pick any number to plug in for x here, but the range, as you see, this is going towards 0, but it's never going to cross 0. You can keep plugging numbers in to x, but it's never going to make it 0 or negative. So the only range values here are going to be positive numbers. So the way I'm going to write my domain and range is by doing domain all real numbers. My range is going to be y is greater than 0, because it's never going to reach 0, but it's going to come infinitely close to 0. Anyway, we successfully completed all of the criteria for this example, and now we're done. Graph f of x equals negative quantity 1/2 x compared to the graph of the parent function. Describe the domain and range of f. All right, so I'm going to make a table of values. Okay, and I'm going to start with 0 in the middle, like I always do. Okay, and now I'm going to plug in my values. I'm going to start with 0 because it's the easiest. Okay, 1/2 to the power of 0 is 1, and then I apply the negative sign to get negative 1. Okay, now I will start with 1 here. Okay, 1/2 to the power of 1 is just 1/2, and then I'll apply the negative. So that's negative 1/2. And if you see, I'm just multiplying this by 1/2. So to get to this value right here, I'd get negative 1/4. And then going the other way, I'm multiplying by 2, the reciprocal of 1/2. So times 2 would give me negative 2, and then negative 4. All right, so now I just want to plot all these points. Okay, so we can see our graph right here. So I'm going to draw a sketch through it. So this is a pretty basic sketch of my graph. Once again, you could try to draw a smooth curve through this if you wanted to, like this. Okay, either way works. Now I want to graph the parent function on here so I can compare them. Okay, the parent function, once again, is just whatever this number being taken to the power of x is without anything on the outside of the parentheses. So I can just get rid of this negative, and my parent function is just going to be positive 1/2 x. So I'll call this g of x equals 1/2 to the x. And my table is going to look very similar, except for all of my y values, instead of being negative, they're just going to be positive, right? Because I just got rid of that negative here. So I'm just going to recreate this table. Okay, now I'm going to plot these. I'll plot these in red. So now I'm going to sketch my curve through this. Okay, and if you see, I forgot my arrow here. And if you see here, this is a reflection in the x-axis, which makes sense. Okay, I have something outside of my function here. This negative sign is outside of my function. And since it's outside of my function, it's going to be a vertical change. Okay? And the negative sign just means it's reflected. So a vertical reflection is a reflection in the x-axis. Remember, the x-axis is acting as a mirror. Okay? Now I'm going to describe the domain and range of f, our original function here. The domain is still going to be all real numbers. I can plug any number in for x. Okay? And then my range is going to be all the numbers that are less than 0 here. Okay? So we're writing that out. That looks like this. Domain, all real numbers. Range is going to be y is less than 0, because I want all my values to be below 0. Anyway, now we're done with this example. Graph y equals 4 times 2 to the power of x minus 3, all plus 2. Describe the domain and range. Okay, well, I'm going to write this in the form of y equals a times b to the power of x minus h plus k. This might look familiar. This looks like absolute value functions that we have graphed, okay, where h and k represent a translation here. Okay, h would be our horizontal translation, and k would be our vertical translation. And it works the same way for exponential functions here. So there's a couple of different ways you can graph this. One way is to graph the original function without this translation, just graph y equals 4 times 2 to the x, and then translate what your graph is, in this case 3 units right, and then 2 units up. Okay? But I think that there's an easier way. I'm going to make a table, but if you've noticed, my last tables I had 0 as the center of my table. Now we want whatever is going to make this whole entire exponent equal to 0 to be the center of my table, and you'll see what I mean in just a moment. So if you look here, I'm going to make the center of my table not 0 this time. I'm going to make it 3. Because 3 is going to make this whole entire exponent equal to 0, and I think that's the easiest one to work with. And then I'm going to surround my middle value here, which is going to be 3, with numbers above that and below that. Okay? So I'm going to put 3 here, because that's going to make my exponent 0. And then I'll go 4 and 5. Then I'll go 2 and 1. Okay? So now, when I plug in 3 here, okay, I get 3 minus 3, that's 0. So 2 to the 0 is 1. So 4 times 1 is going to be 4, and then 4 plus 2 is going to be 6. So I get 6 here. Okay. So now that I've got my first y value, I'm going to find another y value here. Okay. So I'll plug in 4. So 4 minus 3 is 1. 2 to the power of 1 is 2. 2 times 4 is 8, and then 8 plus 2 is going to give me 10 here. Now I'll do 5. 5 minus 3 is 2. 2 squared is 4. 4 times 4 is 16, plus 2 is 18. Okay, then I'll do 2. 2 minus 3 is negative 1. 2 to the power of negative 1 is going to be 1 half. 1 half of 4 is 2. 2 plus 2 is going to be 4. And then I'll plug in 1. So 1 minus 3 is negative 2. 2 to the power of negative 2, well, that's 1 over 2 squared, which is 1 over 4. 1/4 times 4 is 1. 1 plus 2 is going to be 3. All right, so now I have my table. Okay? And you can figure out the pattern here without doing all that math, but it would involve subtracting 2 here from all of your y values, and then you could figure out what the pattern would be for the common factor. Anyway, I'm going to plot all of these. So I plotted my points, and now before I sketch my curve here, I just want to note that if we just had a normal non-translated exponential function, we know that it would try to reach 0, but it would never get there for the y value. Okay, same thing's going to happen, but I'm translating this 2 units up, so this is actually never going to reach 2. Okay, so I will sketch my graph and make sure not to cross 2 here. So this is a pretty decent sketch of this exponential function. Now I need to describe the domain and range. So my domain, once again, is going to be all real numbers because there is no number that I can't plug in for x here. And then my range is going to be not y is greater than 0 this time, but because it never is going to reach 2, it's going to come really close to 2, but it's never going to reach 2. My domain is going to be y is greater than 2. So I'm going to write that down now. All right, so I've successfully graphed this and described my domain and range, so now I'm done with this one. An exponential function g models a relationship in which the dependent variable is multiplied by 1.5 for every 1 unit the independent variable x increases. Graph G when g of 0 equals 4. I'm going to make a table here. Here's my table. All right, so I like to have 0 in the middle for my table, so I'm going to put 0 in the middle, but I know g of 0 is going to equal 4 in this case. So I'm going to have 0 and 4. Okay. Now, what this is saying is every time I increase the independent variable, which is x, by 1 unit, okay, so if I'm increase means adding 1, okay, I'm also going to subtract 1 here. Okay. Every time I add 1 to x, I'm multiplying y, or my output, by 1.5. Okay? So my initial value is 4 here. So to get from this value to this value, I just have to multiply by 1.5. Well, 4 times 1.5 is going to be 6. Okay? And then 6 times 1.5 is going to be 9. And you can do this out if you weren't sure. Now that I'm noticing, I know I can fit one more value over here because my y value goes up to 16. So I'm going to extend my table. Always fine to extend your table. So when x is 3, I just have to multiply this by 1.5 again. Well, 9 times 1.5 is going to be 13.5. Okay. An easy way to multiply by 1.5 is just multiply by 1 and then add half of it. So 9 plus 4.5 is 13.5. Anyway, going the other way, I'm actually dividing by 1.5 here. Okay? So 4 divided by 1.5, that's the same thing. Dividing by 1.5 is the same thing as multiplying by the reciprocal of 1.5, which is 2/3. Okay, so 2/3 of 4 is going to be 8/3, or 2 and 2/3. And then I could take 2/3 of this, okay, going the other way. And 2/3 of 8/3, well, 2/3 of 8/3 is going to be 16 over 9, which is going to be 1 and 7 over 9. And you could keep going here, but I think this is plenty of points for my table. Okay? Now I'm going to plot my points. Now I've plotted all my points, okay, and I know that I'm going to be never reaching 0 here because I could keep multiplying by 2/3, aka dividing by 3 over 2 here, but I would never reach 0. I can get infinitely close to 0, but never reach 0. Okay. So anyway, I know that I'm going to stop my curve from happening right above 0 here, okay, and then I'm going to sketch my curve right now that goes through my points. So the curve is going to look something like that. So now I've successfully graphed this function given the information above, and now we're done. For an exponential function of the form y equals a times b to the x, the y value changes by a factor of b as x increases by 1. You can use this fact to write an exponential function when you know the y-intercept a. The table represents the exponential function y equals 2 times quantity 5 to the power of x. The y-intercept is going to be the initial value in a real-life problem, okay? And another way to think of that is it's the value of y when x equals 0, and if I plug 0 in for x, b to the power of 0 is just going to be 1, so the y-intercept is just going to be a times 1, or just a, so that's why this is going to work out the way it is. The graph represents a bacterial population, y, after x days. A. Write an exponential function that represents the population. B. Find the population after 12 hours and after 5 days. All right? So first we need to write this exponential function. Okay? And I see right away on the graph that my y-intercept is going to be 3. Remember, the y-intercept is the value of y when x equals 0. And if you remember, my y-intercept is going to be this a value in y equals a times b to the x. So I know that my a value is going to be 3 here because that's my y-intercept. Okay, so I know that I have y equals 3 times b to the x. So now all I need to do is figure out what my b value is. Okay? Well, if you remember, the b value in this case is the number that is being multiplied over and over again, hence the exponent. Okay? So I can take all my y values and look at the pattern here. I'm going from 3 to 12, and then from 12 to 48, 48 to 192, 192 to 768. You might be able to tell that each time you're multiplying by 4. So the number that is being repeatedly multiplied is going to be 4 here. So that has to be my b value. Okay? So I know my answer is going to be y equals 3 times 4 to the power of x. Okay, there's another way to do this if you weren't entirely sure. You could just plug in some x and y values and set up a system of equations. I'll just do that really quickly here. So you could set up, let's say I plugged in the ordered pair 0, 3, and then 1, 2. So first I'll do 0, 3. So that would be 3 equals a times b to the power of 0. Okay, well, b to the power of 0 is just going to be 1, so I just get 3 equals a. That's y, we know that's going to be the y-intercept here. Next, I could plug in the point 1, 12. Okay, so my y value would be 12. Okay, my x value would be 1, but I already know my a value. My a value is going to be 3. So then I could do 12 equals 3 times b to the power of 1. Well, b to the 1 is just b. Then I could divide 3 on both sides, and I would get 4 is equal to b. And then plug that all in to get this exact same equation. So both ways worked. Okay, so that's how to find our exponential function, y equals 3 times 4 to the x power. But now I want to find the population after 12 hours and after 5 days. So notice, x is the amount of days. And if we go back up here, this is the amount of hours. We want to find the population after 12 hours here. Well, 12 hours is just half of a day. So this is when x would be 1/2. Okay, so I can just plug 1/2 in here and find my population after 12 hours. Okay, so this is going to be y equals 3 times 4 to the 1/2 power. But if you remember, the 1/2 power is the square root. Okay, so the square root of 4 is going to be 2. It's going to be 3 times 2, which is equal to 6. So we have 6 bacteria after half of a day or after 12 hours. And then our other value we wanted to check was after 5 days. Okay, well, we don't have to change that. So I can just plug in 5. And I will do that over here. So I get y equals 3 times 4 to the power of 5. Okay, and then, well, 4 to the power of 5, you can multiply this out. Okay, if you have access to a calculator, you could do it. I happen to know that this is going to be 1,024. Okay, and then that's going to be multiplied by 3. So I just have to do 3 times 1,024. Okay, that's going to be 3,072. Once again, you could have done all this math out or using a calculator. Anyway, we found the amount of bacteria that are in the population after the amount of time, and now we're done.